In this problem, we will apply the open system entropy balance to a multi-component process. And so here we're dealing with a process that takes atmospheric air and compresses it and heats it before it goes inside a chemical reactor. And so the inlet air is at ambient conditions at 20 degrees Celsius and 1 bar. And this air is going to undergo a two-stage process. In the first stage, it goes into a compressor, where the pressure is increased to 5 bar. In the second stage, it then goes into a heater, where it's heated at constant pressure to a temperature of 400 degrees Celsius. If we assume that we can treat the air as an ideal gas, with a heat capacity of about 21 joules per mole Kelvin, we should also assume that the compressor is going to operate adiabatically and reversibly. Based on these assumptions, what we want to determine are the amount of work that must be supplied to the compressor, and we also want to identify the temperature of the gas leaving the compressor, or the air, right? And in part B, we want to determine the amount of heat that's needed for the heat exchanger in order to heat the air to a final temperature of 400 degrees Celsius. Based on the information in this problem statement, what I want you to do is to pause the video here, and I want you to sketch out the process flow diagram. Based on this process flow, or based on the information in this problem, we could sketch out a process flow diagram that looks like this. And so we sketch the two components of our process. We have our compressor here, which is going to input some sort of shaft work into the air in order to change both its pressure and its temperature. Then we have a heater that inputs some sort of heat in order to change the temperature to 400 degrees Celsius. Right? We're assuming it's an ideal gas, so we know that for CV, to get CP, all we have to do is just add the gas constant, R. And so based on the information in the problem statement, and based on how we sketch out the process flow diagram, we know that we have 5 unknowns. And so in order to determine all of the unknowns in our problem, that means we're going to have to derive 5 different equations as well. Before we proceed to our balances, we should list our assumptions. And so for this problem, because we have the air crossing the system boundaries of the compressor and the heater, we're going to treat both components of the process as open systems. We don't have any indication that temperatures or pressures are going to be changing with time, so we'll also assume that we're operating at steady state. We're dealing with an ideal gas, or we're assuming we're dealing with an ideal gas. We're also told in the process statement that the compressor is adiabatic, and so that means for the compressor, the heat term, specifically for the compressor, is going to be equal to 0. Also for the compressor, we're told that it's reversible, or it's operating in a reversible fashion. And so mathematically what that indicates is that in our entropy balance, the entropy generated term is going to be equal to 0. We're not going to worry about changes in kinetic or potential energy. And when it comes to our reference states, we're just going to use the inlet conditions for the entire process. So Tref is going to be equal to T1, Pref is going to be equal to P1, and our reference phase is going to be that of a gas. Okay? All right, and so using those assumptions, we could then simplify our balance equations. And so in this problem, in part A, we want to figure out the shaft work and the temperature for the compressor. And so here, our strategy for the problem is we're just going to focus on doing balances around the compressor first. And so we'll proceed through our balances in the typical way. We'll first start with the material balance. There's no reaction. We're at steady state. And so that tells us that the input to the compressor is going to be equal to the output. Therefore, our input is equal to N1, our output is equal to N2, and so that means that N2 is equal to N1, which is just going to be that 1 mole per second. All right, and so from our material balance, we have that the molar flow rate is constant. Let's now move to the energy balance. We're dealing with an open system, so we'll use the open system form of the energy balance. And we have our energy terms due to the streams going in and out. We're not going to worry about kinetic energy, and because we're steady state, nothing is going to be a function of time. Also, we're assuming that the compressor is adiabatic, so that term is 0. And so the left-hand side of our energy balance is equal to 0, and on the right-hand side, what we're left with is the shaft work, the enthalpy of the stream going in, and the enthalpy of the stream going out of the compressor. And we know that the molar flow rates here, N2 is going to be equal to N1. And so we simplify down our energy balance to this statement. In the end, what we want is the temperature of the stream coming out of the compressor. And so in this energy balance, the way we're going to relate it to temperature is going to be through our enthalpy terms. And so based on the definition of enthalpy, we know that the enthalpy is related to temperature through the constant pressure heat capacity, where we're going to integrate it from Tref to the temperature of the actual stream. And in this case, we know that Tref is, well, actually, I'll keep it there for now. Stream 2, it's the same sort of thing. So if we go back to our energy balance, we have this. We could factor out the CP since it's in both enthalpy terms. We'll have T1 minus Tref minus T2 minus Tref. Trefs cancel. And so if we rearrange the equation, we get that the shaft work is equal to N1 CP T2 minus T1. Okay? Alright, and so in the end, we want to calculate the shaft work and the temperature of the stream coming out of the compressor. And we see here from our energy balance, we actually have 2 unknowns at this point. And so what this tells us is that from the energy balance alone, we can't solve for all of our unknowns. Okay? So what I want you to do here is I want you to pause the video and I want you to think about what you should do next.